Hello everyone, Tosh Khan here. Most of you have met me before, and I'm here to talk to you today about the creation of a self-updating local reference sequence blast database. And I know that's a little bit long-winded, but we'll get to that in a minute. So a common problem today, both with researchers and repositories alike, is that as we sequence more and more, the consensus as to what exactly a gene is becomes more clear. So the question then becomes, how can we keep our in-house information aligned with what NCBI has available? NCBI will release updates very frequently, which is great for when you have a single solitary sequence. You can reach out to NCBI and you can, blast your single sequence and you'll get several alignments back and it'll be this nice, beautiful web format. But that becomes a little more difficult when you have several thousand sequences, for example. There was an example earlier where a student had 40 sequences he analyzed, but what if that was 4,000? It would be a little more impractical to ping NCBI for every single one and sort of look at the web layout and copy and paste it and begin your analysis there. So that sort of creates this need to be able to interact with NCBI in a way that is not web-based. NCBI has query limits and restrictions. So even if you want to send, I think it limits it to about 3 URL pings a second, and that sounds like a lot, but after a while it will kick you off, especially if you run it at sort of peak hours for NCBI. So you need to create a way to have this information locally, and my goal is to make that a little less painful. So what NCBI does is they make reference sequences for genomes available, usually for daily download. Sometimes it'll be every few days. Whenever they have a significant update, they post it. And this is supposed to be how large environments can interact with the sequences and sort of complete the analysis that they need. This process can be a little bit more time consuming, so it's my goal to sort of make this automated and to sort of always have the latest and greatest in reference sequences downloaded locally so you can do whatever type of analysis you might need. So why don't I go through and actually just show you so here is NCBI's FTP site. It's got tons of stuff on it. I haven't looked through all of it. You can see sort of some of the things that I have clicked on, genomes, refseqs. What we're interested in today is the reference sequence, and this is what's considered sort of the most up-to-date information the scientific community has if you want gene expression or knockouts or whatever it is that you might be doing. You can see there are several different species here. I think the tool that I'm talking about today is probably most useful for mouse and human, just because those are the ones that have tons and tons of data. And for example, let's say you're going to begin an experiment. Well, this is where I work. This is a plasma repository. This is sort of how the idea was born. And let's say you want a gene of interest. Okay, good enough. And it's going to pull up all these results for you, and you're thinking, okay, which one do I know? Which one do I need? And more importantly, as a repository, how do we provide you with which one is the most up to date? I pulled up 2 here already. You can see this clone has 1,000 BP sequence that's supposed to correspond to MET. And this one has a 4,000 base pair sequence that's supposed to correspond to MET. So how can we let you know which one you should be ordering, which one is the one that's going to get the result that you need? To do that, I'm planning on writing a Python program, or I have written a Python program at this point, that connects to NCBI and downloads the latest human reference sequence and just routinely compiles it into this database, daily, weekly, whatever you want to set it to. And from here, you can begin to flag these types of sequences and say, you know what, this particular construct or this particular gene is the one that you want. It's the one that actually will show you expression for MET. So we can begin to see how I went about that. So here again, FTP site for NCBI. This is where all the reference sequences are located. The relevant files that we're going to need here are the genomic FNA files. One's just for Mac and one's for Windows. So I'll sort of walk you through a bit of this program right now. And what I did is I used Python to ping the FTP site, download the files, unzip them, and then what you're going to need to do is you need to have BLAST local tools. And what BLAST local tools will do is it will compile a database for you so that you can begin to repeatedly get your results, do your alignments, whatever it is that you might need to do. So here, the two things we ask for the user are, where would you like me to put this database locally? And where's the location of your local BLAST tools? So once we get that information from the user, we go ahead and this line of code here just connects to the FTP site at NCBI. Login is necessary, but for NCBI, you can just log in skipping the username and password. Go ahead and make the FTP, scroll to the relevant folder, which is this one here. I mentioned the file type we need, and so all we're going to begin to do is we're just going to say, give me all the file types, and I've written a method that will go ahead and download a file type with a specific suffix. In our case, it is .fna. I have that here somewhere, yeah, .fna here. So it'll download those, unzip them, and it's important, I mentioned earlier, that you need to feed NCBI one single file. So what I'm going to do is I'm going to remove all the unzip files after I've uncompressed them. I'm going to rewrite them to a singular FAFSA file. And from this, I can make a call to the local BLAST database path and ask it to begin compiling my BLAST database. So why don't I go ahead and run you through the command here. So here's where I've asked it to go. This is a previous one that I work with. You'll see the time here is 4:22 p.m. This command here, just running the Python program, feeding it the arguments of where my BLAST database is located to and where I would like it to put the database when it's done. It's going to go ahead and download the reference sequences now. You'll see them up here. We make sure we delete before every time we do this, just so no old files get placed in there. Takes a bit. They're rather large files. And the uncompressed ones are gone, and we've concatenated it into one genomic file. And now we have our BLAST database, just like that. So now when it comes to automation, this is going to be environmentally specific. At some point when I wrap it into GUI or whatever it is that this program ends up being, it can run on Orchestra nightly. For right now, I've done a scheduled task, and basically you can see that it's going to run my program. You can see here it makes the exact call here that we have in the command, and it's going to run that at 3:51 p.m. or whatever it ends up being. So now that you've seen that, let's go ahead and see what the results look like, because that's actually pretty important. So all I've done is just fed a command that basically says, blast my local database. I've asked it to put that in a folder called results. So here's a test sequence. I think I picked ADP, and we'll go ahead and see the results. So they come out in this format. This should look pretty familiar. This is what you'll see on the web. This is obviously unmanageable. This sort of brings me to the future work. I need to format the output of the BLAST database so I can basically retrieve one line. And this way you can begin sort of doing analysis on 300, 400, however many thousands of sequences. If your analysis takes a day and a half, then you feel comfortable running that because that's on your machine. Those are your resources. You know you're not going to get kicked off. So future work, I need to figure out some more time with this sort of formatting the output. BLAST does make that available, but it is a bit of a chore to work through. It wasn't part of this project, but it's something I would like to do in the future. Beyond that, you have to begin thinking. We're working mainly, in my case right now, I'm working with coding sequences and nucleotide databases. The program that I showed you, you can manipulate easily to do protein databases or ribonucleotide or whatever. So at some point I need to figure out what to actually do once I've gotten all this analysis and how to make those judgment calls on this is the latest and greatest. Beyond that, I think what I'm going to do is I'm going to sort of track these databases and compare them against each other and just see how much change there is over time. I think that would be valuable. And obviously, I'm going to make this available publicly. I just wanted to thank Claire Yu, who works at the Department of Genetics. She gave me a lot of consultation on this, the core that I work, for allowing me access to their database and things like that. I work there, so it's in their benefit. Dr. Parker and Ed Friedman for their feedback on my project, and Nampo in Research Computing, who sort of helped me get a little bit better acquainted with research computing and the NCBI tools. That's it. Thanks, guys.